Good morning or good afternoon to everybody. We'll get started with the presentation right away. Thank you for joining us today. I hope this presentation will be interesting to you. My name is Paul Scotchless. I'm the Artificial Lift Product Champion at PCM. I've been in the business for 25 years, the last 2 at PCM, and before that I was in Canada. So I've been around and I've seen a lot of different things, and hopefully I can share some of that experience with you today. Let's go back to the presentation here. Okay, so as usual with our webinars, we can't hear what you're saying. If you have a question, there's a Q&A panel that you can turn on, and you can use that Q&A panel to type in any questions you have or any comments you have. And we'll address the questions at the end of the presentation. All right, let's get started here. So we're talking about monitoring, best practices for monitoring PCP systems today. So first off, what is monitoring? Anything we can do to observe the condition of our system. During most of the presentation today, we're really just going to look at the things that you can measure quantitatively, pressure, temperature, etc. But there's other things you should be looking at as well, such as, is your drive head making strange noises? Do you see leaks? Not just the stuffing box, but any other seals on the drive head or anything like that. Is there anything else just happening around the well that's not normal? Those are obviously things you need to be monitoring as well, just qualitatively. So we'll continue looking at the things that are more quantitative. We can measure things surface or downhole, pressure, temperature, flow rate, vibration, fluid level, etc. Measurements can be automated or they can be manual. It could be somebody reading the pressure gauge on the wellhead and writing that number down. Or it could be an automated system that's recording it into a SCADA system. It could be done real time, or it could be recorded for later analysis. And recorded for later could mean, again, the operator writes it down and at the end of the day it gets put into the system. Or it could be a memory gauge where you don't get the data until weeks or months later. Why do we monitor wells? Main reason usually is to optimize production, which we usually mean to say we want to get the most production out of the well that we can without causing problems, such as running the pump dry or breaking the rods or drive equipment or overpressuring the pump. So we want to get as much production as we can without overdoing it and causing damage. We also like to be able to troubleshoot things if something's not working the way we'd like it to. We want to understand why. And if something fails, we want to be able to understand what caused that failure to prevent it from happening again later. We can also learn about the reservoir. I suspect most of you listening today are not reservoir engineers. I'm not a reservoir engineer, but the reservoir engineers, they can learn a lot from certain types of data that we can collect on the production side. I'll talk a little bit about that later, and that some of that data can be really important to them. So if you can work with them to understand what data they can use and what value they can get from it, it can be overall benefit to your companies. If you can learn about any mistakes that were made during, not so much mistakes as maybe bad assumptions that were made during the design, find out that the conditions are a little bit different than you thought they were in the well, then you can use that information to improve things for the next installation in that well, but possibly also in neighboring wells as well. So what can we measure? At surface, there's some things, and most of these are done by most people. Maybe not done automatically, or they're not recorded, but most people have most of this information. Speed, whether that comes from a readout on the VFD or from a tachometer mounted on the drive head. It should be pretty accurate. The tachometer will be a little bit more accurate than the VFD. There's always error in the VFDs because they're depending on a few things. And one of them is the shiv ratio has to be entered in. So if it's not entered in perfectly, you're going to get a little bit of error on the speed. But unless somebody's really made a mistake entering that data, it's probably good to 3 or 4%. Torque, Most people would get the torque just off the VFD. Again, it's depending on that data being entered correctly for the motor properties and the shiv ratio to be able to get the torque off of VFD. It's not quite as accurate, I suspect. 10–15% is probably a good estimate of the accuracy of that. Come back to that a bit later. Things like wellhead temperatures and pressures. Pressures are very common. Most people are measuring the casing and tubing head pressure. Temperature maybe not quite as much, but if you're in a thermal operation, it's probably something you're looking at. Those can be manual gauges, or they could be connected to a SCADA system. Fluid levels. I've got this in a surface measurement because it's usually measured from surface with an acoustic system. We'll talk about downhole pressure in a minute. So the acoustic fluid level sensors connect onto the casing vent valve. It's usually a manual system. An operator goes out and takes a fluid shot, but there are automated systems available, which can then connect into your SCADA system or your pump off controllers. Flow rate. Most people are not measuring flow rate continuously, but a well test every once in a while. Is that every week? Is it every month? Depends on your company. But getting that information, getting the gas rate and the liquid rate is very useful to have that as often as you can get it. Some systems have flow meters built in. Those may not be super accurate, but they're good enough for the purpose and give you some good information. One comment I like to make about fluid rates is that it's really good if you can get casing and fluid rates separately, and most people don't do that. They'll get a total gas rate and a total liquid rate. Gas in particular, you'd like to know how much of that gas is going through the pump as opposed to how much is going up the casing. But if you don't measure them separately, you don't know that. Liquid, there's usually not liquid coming up the casing, but in some cases there might be, and it would be good to know that if there was. For example, you might have your pump efficiency more than 100% if you're producing liquid up the casing. It'd be good to know why you're seeing that. Fluid sampling. What's the properties of the fluid densities, how much sand is in there, what's the viscosity of those fluids. That's not something you're measuring every day, certainly, but if you get an occasional measurement on that a couple times a year, maybe it would be good to know. For solids, you probably need to measure that a little more often if you're in a high solids application. Downhole monitoring is usually intake pressure and temperature, discharge pressure and temperature, and vibration. The companies that make these gauge packages just include the vibration on there whether you need it or not, so it's something that's available if you're buying downhole gauges. One comment I want to make on these pressure gauges, they say intake pressure and discharge pressure, but usually they're not exactly measuring both of those directly. Usually the gauge is mounted either above or below the pump. If it's mounted above the pump, it's probably measuring the discharge pressure directly, but what it calls intake pressure is probably just the annulus pressure at that depth. So it's not exactly the same as what's at the pump intake. If the gauge is mounted below the pump, it's probably measuring that intake pressure directly, but the discharge pressure is going to be measured through a capillary line to the pump discharge. So there's going to be an offset of a hydrostatic head of the fluid in that capillary line. Those are small numbers in most cases, but I have heard of a case where this did end up in causing a failure because a company had set up their pump off controllers for the gauge being above the pump, and then at some point they changed vendors, and the new vendor was providing a gauge that went below the pump, and this moved the fluid level because they didn't change the settings in the pump off controllers, so it moved the fluid down by about 2 joints. And that was enough for them to be running pumped off, and they had some failures. So it's just something to be aware of. What exactly do those numbers mean that you're getting from a gauge? Just briefly mention fiber optic systems because this is not something we normally see in a PCP application. It's more of a special case, but those allow for measurements of things like pressure, temperature, and acoustic measurements throughout the entire well. So they're reading about every meter. So depending on what your application is, you can put one of those systems in and get some information about, for example, where the flow is coming into your well and things like that. But that's outside of the scope of best practices for a PCP application. It's more of a special case, so we'll leave that alone. For your standard downhole gauges, the typical gauges are wired. There's a cable that connects it to surface, and the communication goes through that cable. There are wireless gauges available, so you can get rid of the cable. Getting rid of the cable is a nice feature because it's often a reliability issue. The cable sometimes is what fails first. It's also during the workover, someone has to be banding that cable to the tubing joints. There's a lot more effort involved during the workover, so wireless makes sense. The downside with wireless, of course, is now you've got a battery downhole, so you have a limited lifetime there. For deeper wells, you may need to have repeaters. So you have your gauge downhole, and then there's some repeaters that go 2 or 3 of them on the tubing on the way up to the wellhead to be able to continue that signal to surface. There's also memory gauges. Those are good for certain applications, but not for any kind of control, obviously, because you don't get the data until the next workover. Data collection can be manual, automated, stored, or automated and transmitted. So manual is somebody writes down the number off of a gauge or off the VFD panel and types it into the computer at some point later. Or maybe types it into a computer directly, but it'll get uploaded into the network later. Automated and stored, so there could be a data logger at the well, or it could be built into the VFD that's recording whatever gauges are there and storing that locally. And then every once in a while, an operator will go download that and take it back to the office and put it on the network. And then there's the final one, which is it's connected directly into the SCADA system. So there's no local storage. It's all just going right up to the network for immediate accessibility by anyone on the network. Obviously, there's higher costs as you go down this list, but more advantages. If you do the local data loggers, there's a trade-off between how often you can store the data and how often you have to download the data into the back onto the network. Because if you're storing it every minute, for example, you might have to come out every couple of days to download that data because it'll fill up the local storage. But if you store a data point once a day, then maybe it can last a month before it has to be downloaded, depending on how much memory there is locally. So how do you get value from measurement? There's a lot of different things you can do. I'm not going to go through this list in detail, but there's some obvious things on here. As usual, the slides will be posted in a couple of weeks, so you can have a copy of this to refer to it later. But for example, if you want to know what your pump's volumetric efficiency is, because I need to know if I've got the right rotor size, if I have the speed and the flow rate, I can calculate the efficiency, and then I can decide is that too high or too low. If I know the differential pressure on the pump, then I can, and the efficiency at the same time, I can figure out where I am on the pump curve and decide if, again, is my rotor sized properly for that. If I have torque measurements, I can use that to protect the rod string and shut down if there's high torque. I can also use that in some solids applications to determine whether I need to call out a flush by, but to prevent the well from going down. Again, there's a lot more information you can get from this. Fluid shots give you pump submergence, which tells you if you have some room for optimization. So there's a lot of things we can do with the data. So we'll go into some of these in a little bit more detail. So optimizing performance is the main thing that people want. We want to get as much production out of the well as we can without resulting in an early failure. So we want to make sure that we're not overloading the equipment and we're not running the pump dry. So the normal procedure is we want to adjust the speed to maintain a small fluid level above the pump. How much fluid level depends on how consistent the operation is and how often we're measuring and things like that, and how accurately we can measure. But in an ideal world, we probably want at least 1, maybe 2 joints of fluid above the pump, but that's an ideal world. If you don't have good accuracy of your measurement, then you'll want to target a much higher level. Or if your reservoir is inconsistent and sometimes produces more, sometimes less, then you need to make sure that you always have at least that much fluid level, which means in sometimes it's going to have a lot more. Again, the more we can draw that fluid level down, the more production we get. So that's the advantage, but we want to make sure we avoid that failure. That can be done in various different ways. Is it the simplest system is someone takes a fluid shot, determines there's lots of fluid above the pump and speeds it up. Now you have to be very careful with that. Yes, if you see lots of fluid above the pump, you can speed it up, but you don't just speed it up and walk away. You speed it up and you take another fluid shot and look to see how it reacted. Maybe take a third one and see, is it stabilized? If it's not stabilized, if it's the fluid level is still going down, then you need to wait, because if you've sped it up too much, you could end up damaging your pump, having the failure. On the other hand, if you see there's very little fluid above the pump, then you're going to slow the pump down. And again, you want to then do another fluid shot to see how much have you slowed it down enough to be safe. If you have downhole gauges, then you can have that feed into an automated system as well to try to target a certain downhole pressure. I'm always be cautious about this though, because if you're using downhole pressure alone, you better make sure that your casing head pressure is very stable. Because if you're feeding into a flow line, for example, your gas production is in a flow line and that pressure is not constant, any changes in that casing head pressure will change the downhole pressure without changing the fluid level. So you have to be very careful there. When you see an increase in pressure, is it because there's more fluid available, or is it because the casing head pressure went up? So be very careful with that. If you can include both of them in that control system, that's best. And then some systems use the flow rate measurement. And the way those work is they do steps, continued steps up and down in the speed, and they look for changes in the flow rate. If you increase your speed a little bit and you see an increase in flow rate, it's good. You can probably increase the speed a little bit more. If you increase the speed a little bit and you don't see an increase in flow rate, then you need to back off on that speed. That's the simple explanation of those systems. For reservoir data, this is, again, the reservoir engineers can get a lot of value from certain types of data. So if you're working with those guys in those teams, they can get some value from this, and maybe that they can work with you on the budgets for paying for some of this instrumentation if it's something that they're interested in. Every time you shut a well down, the pressure builds up in the downhole, and measuring how it builds up over time. They have calculations they can do with that gives them lots of information about the reservoir, permeability, skin effects, reservoir pressure, size, interference of other wells. There's lots of things they can get out of that data. And then, so that's during every shutdown, but even during operation, if you run at some different flow rates, so just by running at a few different speeds for a couple hours or whatever, if measuring the flow rate and the pressure downhole, and how the pressure reacts to changes in speed, they can get more information off of that as well. And some of this is useful to you as well for your optimization, because you can use it to understand the IPR of the well and then appropriately design to get the maximum production from the well. Understanding the current performance of the pump. Again, there's lots of different things you can do here. Flow rate and speed give you efficiency, like I said. If we add differential pressure, we can look at where you are in the pump curve and where should you be on the pump curve. If you have torque information from the VFD, you can use that to protect the rod string. So if there's a spike in torque or something like that, you can make sure you don't break the rods by shutting down in time. Some people use it to, when they have high solids, they see increases in torque over time, and they will go out and schedule a flush by to clean out the well before the well goes down. If you have vibration measurement, you can detect abnormal conditions, whether it's a space out problem, too high or too low can increase vibration. If there's a bent rod or something like that, that can cause vibration. Sometimes you can see when a pump is about to fail. You might not be able to prevent the failure, but you can at least schedule a workover. If a pump really starts vibrating, and there might not be anything you can do about it, but you can plan for its replacement. But vibration can also be used to select an appropriate speed. There might be certain speeds where vibration's higher and certain speeds where the vibration's lower. So you want to run in one of those speeds where the vibration is lower. And it's not always just higher speed equals higher vibration. I was on a well once where we were measuring that at 300 RPM, 350 RPM, and 400 RPM. The one with the lowest vibration was actually 350. So if we either sped it up or slowed it down from that, we saw higher vibration. So it gives you, if you're worried about vibration, then knowing what that value is, you can find a speed that gives you the lowest value. And again, I talked about when you have the data, you can use that to look at the models you're using for your well and see can they be improved? Can you tweak the inputs a bit to better match reality, and therefore help you do better designs in the future. Failure prevention analysis. You probably can't prevent a lot of failures. Some you can, like high torque failures, overpressuring the pump if you've got differential pressure gauges. Those failures you can prevent very easily through monitoring. If you're not getting flow to surface, there's something wrong and you need to change that if you don't want to be pumped off. But there's other types of failures where the monitoring may not prevent it. There's something goes wrong downhole and the pump fails. But having that data makes it easier to figure out what happened. Why did the pump fail? And what can you do to avoid that failure next time? So in advance, you don't know what the failure is going to be and what data will be important. So the only thing I can recommend is to collect as much data as possible, because some of that information could be very useful later on, but you don't know which data is important. So it's up to you to determine how much data you're able to collect, of course, and how useful it's going to be to you. But the more data you have, the more information you have on doing a failure analysis. So what is the best practice for monitoring? I don't have a single best practice I can give you, because every operation has to find its own balance between the costs and the value obtained, and considering the reliability of the systems as well. So there's cost involved with all instrumentation, whether that's the CapEx of buying the transducers, the cables, the SCADA systems, whatever you're using. And then there's OpEx for labor in terms of going out and taking fluid shots, recording the data, downloading from the data loggers, and whatever maintenance. And of course, you're collecting data, someone's got to analyze it. There's no point in collecting if nobody's ever going to look at it. So there's time and effort involved in that. But there's a lot of value you get from that. You can get higher production. If you've got a good pump off control system that's accurate, you can maximize that production. You can get greater overall recovery from your reservoir, fewer failures. All these things are add a lot of value to your system or to your company. It's my opinion that you should be looking at value not for just right now, but for the future. What's the overall maximum value you can get from this well over its life? That's my feeling. I know a lot of companies are looking short term, but try to think long term as well. And it may change your decisions on what things are worthwhile. Having the monitoring will increase the reliability of the system if you're using it properly, because you can prevent some of those failures. But you also now have an additional point of failure. What happens when the monitoring fails, but the pump is still running? Especially if you have downhole gauges and you lose those. If you have a pump off control system based on downhole monitoring, and you lose the connection to those gauges, or the gauges fail, what do you do now? So you need to have a backup plan. You're probably going to have something that's maybe not quite as accurate. You're going back to now fluid shots or something like that. So you're probably going to have to slow down a little bit, produce a little less. You're not going to be able to get the same performance out. Either that, or you keep running at the same speed, and when the pump fails, you can replace the gauges as well. So those are decisions you have to make. So just a quick summary of some of those things we can do. We can optimize the production, get as much fluid out of the well while protecting your equipment. So you're looking at, again, trying to get the lowest fluid level in the well without pumping dry, and also making sure you're not overloading things like the rods or the drive system, or overpressuring the pump. You're analyzing the performance of the system in the reservoir, so you can, again, try and maximize the value of that well through its life by improving the designs in the future and getting the optimum production from the reservoir. Analyzing failures, always good to know what caused the failure so you can prevent it from happening again. And I'll just again mention on the first slide, I talked about the things you couldn't measure. Is the drive head making funny noises? It's things like that. Those are important as well. So having an operator physically present on the well every once in a while to look for those things is always good. So just in conclusion, there's a lot of things you can monitor and record. It's up to you to decide the value from that, if the value is worth the cost to you. In some applications, it may be very important to have some of this data. In other operations, maybe it's much less so. So it's up to you to determine what level of monitoring gives the best value for your operations. And I do think it's very important to consider the accuracy of your system. Like I said, if you're doing a fluid shot once a month, you probably need to target a much higher fluid level above your pump than if you have a downhole pressure gauge based system that's reading every minute and making, changing the speed based on that. Then you might be able to target a very small amount of fluid above the pump. But again, how accurate is those systems? If you're using a torque based system, I know there's systems out there that exist, companies that sell those. I think you need to have a much bigger safety factor on those because the torque measurements aren't as accurate. So it's just something to consider. So some overall best practices: if you measure it, record it. So things like flow rate, speed, torque, and fluid level, really important things to have these numbers. Every time you got a well test that gives you a flow rate, it should be recorded somewhere. Every time most systems, unless you're using a pump off controller that's automated, the speed stays constant until somebody changes it. So every time someone changes it, it should be recorded. If you have the pump off controller, it should be recording its changes as well. Anytime an operator reads the torque off the VFD, he should be recording that as well, or even better if it's recorded automatically. Every fluid shot should be recorded. It would be really nice if when they're doing a well test and they're getting that flow rate, that someone takes a fluid shot at the same time, so you have those two data points at the same point in time. So many times I get data from companies, and you can see you've got a flow rate at one time and a fluid shot at another time. Might not even be the same speed, but you never get, or it seems that you never get a complete picture at one point. So I would recommend that if you're doing a well test, take a fluid shot at the same time so you have everything at one point. In general, you're keeping enough fluid over your pump to make sure it never runs dry, based on things like how much variation there is in the reservoir. If the fluid level is going up and down, then you need to make sure it's set that your target point is somewhere that on the bottom end of that cycle you still have enough fluid above the pump. How accurately are you measuring? You need to make sure again that if I can only measure it to within, say, 2 or 3 joints, then I need to add that much to how much fluid I have over the pump. And how often are you measuring it? Have a backup plan for if your instrumentation fails before the pump. Record enough data to help with your failure analysis. And every once in a while, check your assumptions about what's the reservoir conditions. When you're designing a system, you're putting in some information about the IPR, reservoir pressure, and productivity index. Are those good assumptions? Your viscosity information, is it the same as what someone found when they did a fluid sample when the well was first drilled? 20 years later, it might be different. So even 2 years later, it might be different. So check that every once in a while. So thank you very much. We'll go into the Q&A session here. Now there is a time delay on this. So by the time we get to the end of this presentation where we are now, there could be a minute or two difference between when I'm talking and when you're hearing me. So answer your questions right away, because at the end of the presentation, if I say, it's time to end, you could be typing a question there and I won't see it until after it's too late. So please put your questions in early. And we will now proceed to go through and answer them. Okay, so we have a couple of questions. We don't have a lot of questions so far, so please go ahead and continue to put some questions in. I just will put a quick comment on there. Alban has put in a link to a survey. You'll see it in the Q&A panel as an announcement. Please, I would appreciate it if you could answer that survey. I think this is the 6th webinar we've done. So you might have attended one of them, or you might have attended all 6. Doesn't really matter. I'd love to get your feedback on this. So, all right, let me go through, start answering questions here. Is there a reference point for vibration depending on pump type? Vibration is one of these things that it's totally random. You change anything in the system, the pump, the rod, you change where centralizer is, you change how the tubing is centralized in the casing. anything like that. Even changing the fluid level can change the vibration. So I'm afraid there's no reference point on that. If you're measuring vibration, then you can look at for your particular system, do you think it's too high? If you're measuring on several wells, and you can see, is there one well that's more of a problem than others? But other than that, unfortunately, there really isn't a reference point. It's, you can have to build your own guidelines on that for your application, because everything's different. A vendor usually provides min-max recommended speed for pump installed. In reality, we saw sometimes surface amps and pressure fluctuating more at higher RPM, sometimes at lower. So it's possible to figure out where this comes from. Assuming if submergence, maybe. Yeah, that's an interesting question. If you have enough data, you might be able to. I suspect you're probably not going to have that data. Is it a natural frequency if you're seeing higher fluctuations, higher vibrations at certain speeds? It's certainly possible, yes. But what do you do with that information? That is a question. If the vibrations aren't causing you any problems, don't worry about it. But if they are, I mean, for me, vibrations, the biggest problem I'm worried about with vibrations is actually breaking something downhole, usually the tubing, if it's vibrating really badly. So if you're not having those types of failures, maybe it's not a big problem for you. If things are fluctuating a lot, if you can operate at a speed where things are not fluctuating so much, that's better. I mean, a PCM, we put on our data sheets for our elastomer pumps 50 to 500 RPM. That's a huge range. You can operate anywhere in that range. Most people try to stay away from the really high speeds, of course. But anywhere in that range is fine if your surface system is designed for that and you're not seeing problems with vibration or things like that. The rule of thumb generally is, the higher speeds, the pumps might not last quite as long, but there's certainly applications where people do run at those higher speeds. I hope that answers your question. Natural frequencies are really hard to predict. They will occur. You will find certain speeds where there's more vibration, there's more fluctuations. I would normally recommend not operating when you see at that speed, and go a little bit higher, a little bit lower, just to avoid being in a natural frequency. Which fluid level range do you recommend? And again, that comes back to the point I made on the last slide there about it depends on how variable your conditions are in your well and how accurately you can measure things. If you've got everything's nice and stable and you've got good accuracy on your measurements, then maybe only a joint or two of fluid above the pump is enough. If you've got a very unstable condition, or you're not able to measure it very often, if you're taking a fluid shot every month, but that the fluid level changes more often than that, then you need to have a lot more fluid. So it really depends on your application. But certainly when it gets down to a minimum, I'd say one to two joints of fluid above the pump. But that's in an ideal case. And in many cases, you might require more than that. Next question. Assuming constant inflow and no foam, what's the minimum submergence you'd like to see with a fluid level shot? Well, again, I think I just answered that. Does that minimum submergence you're comfortable with decrease with a metal PCP? Well, there's a good question. With the metal PCPs, you no longer have to worry about cooking an elastomer if it's running dry. But still, there's a lot of friction torque inside a metal PCP, and they will generate a lot of heat, and that's going to affect the metallurgy in some way if it gets too hot. So a metal pump can certainly run dry for longer than an elastomeric pump can, but it's not something you want to have. And that's the same thing is true for even rod pump systems. I think in a rod pump, there's nothing there that can be damaged if it's running dry, but it's still not good for them. So does this minimum submergence decrease with metal pump? Yeah, probably a little bit. I can maybe not need so much safety factor, but I still want to try to avoid running dry. Is it common for a problematic natural frequency to be present? You try to predict it or just have to monitor you? First thing I'm going to say about vibrations, problems with that, you can't predict them. There's just any kind of theoretical models for that get thrown out the window when you get into a real well.
because you just can't measure everything accurately enough to be able to predict that. All you need is one little dog leg in the well that's not measured, and there's a contact point there, and then yeah, it doesn't work. So you're not going to predict it, you're just monitoring it. Is it common for a problematic natural frequency to be present? I'm not sure how common it is. You're going to see natural frequencies though. If you're measuring downhole vibration at different speeds, you're going to see different levels of vibration. How often is it problematic? I'm not sure. But I've certainly seen some cases where, you know, at 350 RPM, you saw more vibration than you did at either 300 or 400 RPM, things like that. So it does happen that you get these. Was it a problem? Not necessarily. But it certainly, you know, if those vibrations get severe, then yeah, absolutely. Then you're going to want to make sure you're avoiding those natural frequencies. Someone says, I'm familiar with cable downhole sensors. What are some companies that have data loggers and wireless transmitters for downhole sensors? Trying to remember, I don't remember the name of the company that I saw recently that did this. I'm sure there's multiple companies out there, and I was looking at a website recently for one, but unfortunately I don't remember the name. We'll just have to do some Google. It was an acoustic-based system, so if you Google for acoustic downhole gauges or something like that, you might be able to find that. So sorry, I can't answer that directly. If you email me offline, I can try to find that information and share it with you. Can you identify natural frequency issue at surface? Well, if it's a really severe one, yes. Probably most of the time, not necessarily. It depends on where that vibration is happening. If it's happening at the pump, and it's 1,000 meters down and you're a deviated well, you're probably not going to see those huge vibrations at surface. If it's a misalignment in the polish rod, then yeah, you're gonna see the drive head shaking. If you're seeing the drive head shaking at certain speeds, yeah, definitely there's a natural frequency problem there, and you want to avoid those speeds. If the drive head's shaking at all speeds, there's another problem, and you have to get that fixed. Regarding your suggestion to keep in mind when the gauge is filled, can we make a correlation between other parameters that still record or we have access, such as torque, speed, etc., to predict what kind of submergence we have? In theory, yes. In practice, you're probably going to need a lot more safety factor. So, and there's a couple of papers I've seen out there. One came from India, one came from Australia, where they actually plotted this. They had downhole gauges, yeah, actual differential pressure on the pump, and they had their torque off the VFD that they were plotting, and so you had hundreds of data points on these graphs. And again, there's the two papers out there that I've seen. And if you look at the scatter in that data, if you want to be sure that you've got enough fluid level above your pump, you're going to need a lot of fluid level above your pump because there's just so much scatter in that data. So you can draw a nice trend there that says theoretically what the average torque is for a certain differential pressure. Yes, you can do that if you've got that data. Are you willing to control based on that is a different question. There are people who do, absolutely. I recommend that if you're going to do that, plot that data, look at how much safety factor you're going to need, and base your backup system on that. Because in some cases it's a lot. The bigger your pump, the higher the displacement of your pump, the better it is, because that graph of torque versus differential pressure is steeper, and the uncertainty becomes less of the overall percentages in there. So that's just something to think about. But yeah, if you've got that data, use it, whether it's fluid shots or downhole pressures. Torque, I'm never going to be one to recommend a control system based on torque, but if you've calibrated it based on your downhole gauges and you consider that accuracy level, so how much safety factor you're going to need, then it can be done. But it's not my favorite system for sure. At this point, I've answered all the questions that have been asked. I'll just stick around for a few more seconds. And again, there's a delay here, so you could be typing a question right now and I might not see it before I click the end button here. So I'm just going to wait a bit, and I'm going to remind you there that in that panel, that Q&A panel, you should see the link to this survey. So I hope that you're able to go on there and fill that survey out and give us your feedback on these, and including topics for the next one and what we can do to improve. Okay, well, at this point, if I'm going to start signing off here unless something appears very quickly. Thank you very much for attending, and we hope to see you for the next webinar. And again, I hope you'll fill out that survey for us. And thank you very much. Bye, everyone.